Hello. My name is Kelsey. I'm the evangelist here at Generalized. Welcome. This is our pop-up space. So for the next 6 months, I'm hosting fun events and parties for me, while our permanent space is being built upstairs. For those who are not familiar, Galvanize is a community of entrepreneurs, students, and industry partners. The goal is to get us all together under one roof so we can learn, grow, and work together. And I'd love to explain what that means after Ameen's talk, but I'm just really glad to have you guys here and really excited with our upcoming presentation. So without further ado.
Thank you, Galvanize, for having us. And thank you all for coming. So this talk is titled An Intro to State Channels in Depth. But before we get started, could I get a show of hands in the audience to just help me figure out where you guys are? How many people have heard of Ethereum? All right, that's pretty good. That's pretty good. So how many people have written Solidity code? All right, I see some hands in the back. You guys look familiar. Okay, how many people have heard of state channels before? All right, cool. Okay, my name is Ameen Soleimani. I work at ConsenSys. I work on the decentralized energy project called Co-Tricity, and I also research state channels implementations. And so when people have, I think we're okay. How close am I supposed to keep this? Like, all right, cool. Yeah, so people come in with like crazy ideas about things that they want to build on Ethereum, and in order to build scalable applications on Ethereum today, state channels is one of the ways you can do that, and so try and figure out how it would work. So I'm gonna get started. So why do we care about state channels? So state channels are a design pattern for scalable decentralized applications. So one more time, show of hands, who here knows what a DApp is? It's pretty good, pretty good. So a DApp is just shorthand for decentralized application. I'm gonna use that word a lot. So when you run an application on Ethereum, that application's code will run on every single computer in the Ethereum network. And that is slow, and the Ethereum block times are 15 seconds, and so it takes 15 seconds in order, and sometimes longer if you want multiple blocks, in order to confirm that your transaction took place. It also costs gas because you are using the computational resources of the entire network every time you make any transactions, and every single transaction is public. So state channels is a way to move some of the transactions in your applications off-chain so that they are instant, they can be configured to be private, and they cost no gas. And it works today. It's great. So the agenda for this talk is to sort of give you a broad overview of what state channels are, and then talk more about state channels in depth, talk a little bit about how we secure state channels, and then talk more in the advanced use cases. So my favorite definition of a state channel is a way for two or more entities to privately make updates to some state that only they control. And so if you are imagining the Ethereum global state, so Ethereum is a database, and the database, the content of this database is a mapping of addresses to contracts, and each of those contracts has storage. And so what we are doing with state channels is we are digging into one of those contracts, one small program, and we're taking one piece of state and we are locking it. And we're saying this piece of state can only be updated if these two people agree. And so I'll expand a lot more on that as we go. So the life cycle of a state channel works like this. A state channel is open when two or more participants publicly agree on some initial state. And if the channel is going to involve payments, then money is put in escrow. And so after that, the participants make any number of updates to that state amongst themselves. and only the most recent state is valid, and participants store the state locally. And the channel is closed when any of the participants chooses to publicly finalize the state. So forget about Ethereum for a second. Hi, yes, you have a question? Test.
Better.
Is this much better? Okay. I wish I didn't have to hold this.
Can I start over?
Huh? Can I start over? Yeah.
Is your tech going to be available?
Yes, I can publish this. Yeah. Okay, so forget about Ethereum for a second. Let's all go to a bar. So I'm pretty sure everyone here is familiar with how bars work. And so one common interaction at a bar is opening a tab. And when you open a tab, you escrow your credit card. And so the initial balance at the bar is that we have a credit card and the bar has no money. And after that, there are some state updates. And this isn't recorded in, like, I'm not actually paying for my drink with my card. Somebody's just keeping a record. The bartender is keeping a record of all of the drinks I've ever ordered. And so we make these state updates. And so at some time, I buy one drink, and then my balance is now my credit card minus 10, and the bartender's balance is $10. And sometime later, I buy more drinks, and now I'm minus 50. And at some point, I close my tab. And now my final balance is my credit card minus 50, and the bar's balance is 50. And the card is released from escrow, and the payment is actually triggered and recorded. And so this sort of gives us an insight into like when it makes sense to use state channels. Because we understand why people open tabs. And it's because paying every time for drinks is annoying. Like if I had to pull out my card and go, and then they'd have to sign a thing, and yeah, nobody wants to do that every single time. You only want to do that once. And also, if you want to leave quickly, you just do that too. And so it helps us understand why when state channels make sense, and it's repeat high-friction transactions between the same entities when you have disposable intermediate state. And the reason I say disposable is because when I'm at a bar, they don't care, they don't care what my intermediate drinks I ordered were. They only care about the amount of drinks I had at the end. And so in state channels, that also applies. And also, state channels are useful for privacy, which I won't get too much in this talk, but okay. So when we talk about state channels in Ethereum, I've updated the lifecycle slide. We open the initial state on a smart contract, and the participants make digitally signed updates to that state amongst themselves off-chain. And then they close it by sending this off-chain state to the smart contract, which would then distribute the funds or execute some logic based on that state update. So in our bar examples, that was essentially a payment channel. And so there's a difference between payment channels and state channels. And so a payment channel is something, one more time, raise of hands. Who here has heard of the Lightning Network in Bitcoin? Yes, so the Lightning Network is based on payment channels. Payment channels are a subset of state channels because in a payment channel, the only state that you care about is the balances of two people. And so they allow you to, if they're one-way payment channels, you can pay as you go for content consumption and have micropayments for that. And for a two-way payment channel, you can have peer payments, things like Venmo, Splitwise, or a whole network, which would be like Lightning and Raiden. And so state channels are more general. In a state channel, you can have any state. People have built chess, tic-tac-toe. I've been thinking about building Pong on a state channel, things like that. Anything is possible. So now I'm going to talk a little bit, dig into what actually happens when a state channel is open. In order to do this, I'm going to look at some code, and even if you don't can't understand the code, you will understand how a state channel is opened after you've seen this. Can everyone see this?
Thank you.
Okay. Is this good? Cool. Okay. So this is a smart contract. It's not on the live network. It is just for demonstration purposes, and it is a payment channel manager. And so This is, yes. And so this holds an arbitrary number of payment channels. And so the data of the payment channel is stored in this struct, which is called channel. And that's sort of, you can think of it as an object or a class, and it has some properties. And so the properties that it has are channel ID, the address of person 1 and person 2, and the balances of person 1 and person 2, and the sequence number, which essentially just keeps track of all the messages. It's also referred to as a nonce. And so then there's also this data structure, which is channels, which is basically a mapping of channel IDs to the channel data structure on chain. Okay, so a state channel, or well, a payment channel in this contract would be opened when one person sends a message, calls this open function on the smart contract. And they would do that with the channel ID, so that's here, and the address of the other participant in the state channel, and the value that they want to be held in escrow. And so we do some checks here, and the checks are pretty simple. This makes sure that a channel with that ID doesn't already exist. Then we make sure that you are not the person you are trying to create a channel with. We make sure that you have a payment channel that actually has money in it, and then that the amount of money that you have sent the contract actually matches the amount that you are trying to open the channel for. And so if all of those things happen, if you have specified somebody that's not yourself and sent the right amount of money, then we save this information in the contract and commit it to storage. And then later on, the second participant in the channel would join. And so they would join and specify the ID of the channel that they wanted to join. We would do some checks again. We'd make sure that a channel with that ID exists. We'd check that you are actually the person that was specified by the first person, and that you also have sent the right amount of money to that contract. And so this line here, message.value, that is the ether amount that was sent along with the function call. And so this contract, once the first person has called open and the second person has called join, it's sort of like a Chinese finger trap, where once you put both your fingers in, it's very hard, unless they negotiate, to take them out. And so at this point, the channel is made. And so in order to close this channel, then we would need to send a valid, mutually signed, so both participant 1 and participant 2 would need to send a signature in order to take the funds out. Okay, so I'm going to come back to how to close the channel and take the funds out in just a moment. But before that, I'm going to talk about how off-chain state updates are made. And so just a reminder, okay, actually, I'll just skip this. Okay, so the first thing to know is that when I say off-chain state updates, I'm talking about servers or phones or any combination of the two. Any way that you would normally send a message over the internet, you can send an off-chain state update. And so this can be encoded as JSON or XML or whatever. The important part is that you have to actually digitally sign each of these state updates, and both people have to do it. And so who here knows about digital signatures? I'll do a little quick review about what the important part of this is, and it's like what makes this whole thing work. And so the idea is that you have some state, which is like the balance of person A and the balance of person B, and then you take a hash of that, and then you use your private key, which is known only to you, and you produce a signature. And the signature is just like 0xAD, you know, it's just like some string of numbers and characters. And so that is, the important part here is that that signature that is produced is unique to both the state and your private key. And anybody else can run a program with that, anybody else with the signature and the data can run a program and verify that the signature does in fact match, was produced by your Ethereum address. And also that it matches the state that you are claiming that it matches. So I'm going to go through the flow of what a state update looks like, just break it all down. So on the smart contract, what we saw was A and B both join a state channel. And so on Ethereum, the balances of both A and B is going to be like 100 Ether. And let's say I'm A and I go and buy a sandwich with B, and I don't have any money. And so I want to send B 5 Ether for my sandwich, a very expensive sandwich, at today's prices. And so instead of the traditional way, which is I would send them Ether, instead what I'm going to do is I'm going to send them a message that says, hey, your balance is now 105 in our channel, and my balance is 95, and I'm going to sign that. And so you can see on the right-hand side of this, you have A updates the state and signs, and when I say update state, all that means is that I just produce this new object of the state, which is the new balances. And then I send that to B, and B runs the program to make sure that, one, I gave them the right amount of money, and two, that the signature matches both my address and the state that I signed. And then B would also sign that state and then send it back. And we would both store copies of the latest state off-chain in some database. And so we can do this any number of times, like 1,000,000 times, before we go back to the Ethereum blockchain. And that's why it saves you so much money in terms of paying for gas. Okay, so now closing the state. So the channel is closed when either of the participants sends the final off-chain state to the blockchain, to the smart contract. So now I'm going to go back here and show you what that looks like. All right, so this is the same code as before, but with a few additions. So let me just go to the cool part. All right, so there is a new function called close. And close gets called, so these are the parameters that close gets called with. It gets called with the channel ID, the sequence number, so the channel ID helps to figure out which channel is trying to be closed, the balances of both people, and the signatures of both people. And so this smart contract will, in here, it'll do some more checks. It'll check that a channel with the ID exists. It'll fetch it, so that's what this line does, from storage. And then it'll make sure that the person sending the close message is one of the two people who was a participant in the channel. And then here it will hash the state of the channel, which means it will hash the channel ID and both balances and the sequence number. And just produce a random, well not random, but a string of characters that is unique to all of these numbers. And then off-chain, before this, both people produced signatures on the same hash scheme. And so right here I'm doing the SHA-3 of these 4 parameters. Off-chain, both people would also, when they're producing their signatures, do the SHA-3s of all 4 of these parameters, and then sign that. And so here we can make sure that the signatures are valid from both participants. And if they are, then the channel is clear to send the money out. And so a few more checks, and that's just that the sequence number can't be lower than the channel number, which means if I made some state update to the channel state, I can't submit a state that has a lower number that happened previously. And so this is what enforces that the channel always moves forward and only accepts the latest updated state, but I'll come back to that. The last thing we check is that the original balances, the sum of the original balances is the same as the sum of the present balances, right? So if we both start with 100 Ether in a smart contract, then we both go and submit a signed state to the blockchain saying, hey, we both have 1,000 Ether now. It's going to say no. And so then once we have provided all of this information and it all checks out, then we close the channel and redistribute the balances. And so the escrow it's done. Yeah. Cool. Okay, so I just sort of showed you an example of a payment channel, how to open and close it. The interesting part of a payment channel, I mean, it's just that the state of the payment channel is just the balances of the two people. State channels can be used much more broadly. There are people who are building chess on state channels, as I said, and it sort of has this like similar, it's not necessarily a subset like a rectangle and square is, but it's similar to how Ethereum and Bitcoin have a relationship where Ethereum is more general and Bitcoin is more focused on payments. And so I consider state channels to basically be an I win button for Ethereum development. Now I'm going to talk a little bit more about state channel security. And so as you can see, one does not simply close a state channel. And the reason why is because what if, in my original function, what if I am person A and I realize that if person B submits a later state, like number 2, then I owe them a lot more money. And I don't want to give them a lot more money. I want to only give them 5 Ether. And so what I could do is I could take the first sequence number state and send it to the blockchain. And the blockchain would have no idea. The close function that I had no idea whether or not there were previous states submitted. And so in order to combat this, we use a game theoretic mechanism called challenge periods. And so instead of closing the channel immediately when a valid signed state is sent, we call a request close function, which starts a challenge period. And if there is no valid challenge, which means wrong or we want to settle. And so his second tweet, writing Ethereum smart contracts ends up surprisingly often in a situation where where the code will never be used if everything goes as expected. What he's talking about here is the game theoretic mechanisms that we design. If you make it really unprofitable for somebody to cheat, then they probably won't cheat and your code will never be used. And that's actually ideal in this case. More advanced topics. So what I've showed you is sort of like the atomic unit of payment channels and state channels. And so we can actually do a lot more if we compose them. And so what that means is that for something like a payment channel, we can, let's say if I have a payment channel open with one person, like A has it with B, and I don't have a payment channel open with somebody else, as long as the person who I have a channel open with has a channel open with them, then I can basically send the other person money by going through the intermediary. And so that's what this is. A and B have channels, B and C have channels, and you can see the channel state. And so at time 0, everybody has 100 Ether, and at time 1, in the AB channel state, A has 5 less, B has 5 more. In the BC channel state, B has 5 less, C has 5 more. So net, A has 5 less, C has 5 more, and B is the same. B could also potentially charge a small fee for doing this. The way we secure this multi-hop payment channel network is through the use of hash locks. And so the idea is we want to prevent B from running away with all the money. So if I update the state with B and says, hey, B, you have 5 more Ether, then like what I'm really hoping is that B goes to C and says, hey, C, I have 5 less Ether, you have 5 more. And so if B chooses to, they can just like take that state to the smart contract and just get their money back. And so to prevent them from doing this, we use the hash lock. More on this. So the way this works is that A generates a random number secret, S, and its hash, H of S. And so when it sends the state update to B, it also includes this hash in the channel state. So you can see I added a parameter, the hash is ABC, let's say. And so B then would also send C the state update with the same hash. And the smart contract, we would add a line to it, and it would be designed so that unless somebody has the secret that produces that hash, it will not accept the state as valid. And so A, after B sends C the state update, A would send C privately the secret. And so then C can go to the blockchain and use that secret to close its channel with B and collect this payment. And B now would also have this access to the secret because C published it to the blockchain and therefore it's public, and they can also close out their channel with A and collect their money. So state channels are the atomic unit of state networks. You can chain these things arbitrary length. So I think the emerging topology is that there's sort of a hub and spoke network model where the hubs are identity providers, application networks, and infrastructure providers, and the hubs can charge a small fee for access and liquidity. So slides haven't been updated yet, but the Raiden network launched their first testnet transactions recently, very exciting. Big congratulations to that team. Raiden is a high-speed asset transfer network on Ethereum. I consider it an Ethereum wonder of the world. And so this is just ripped directly from their website. Its payment channels taken to its logical conclusion. It's a network that anybody can join and run a node on. It gives you fast transactions, micropayments. The individual transactions don't show up on the global ledger, so you get privacy. It works with any token that follows Ethereum's token API, which means we're not just sending Ether. That's an advantage over the Lightning Network, is that we're sending anything that matches tokens, which means energy tokens, dollar coins, what have you, you can use on Raiden. And the fees are much lower, which allows you to use micropayments. And so it exists as an Ethereum overlay network. And so what that means is that you're going to have some server, it's going to run an Ethereum node, and then on top of that, it's going to run a Raiden node. And the Raiden nodes all connect, and they all have payment channels open with each other. And so then you sort of do this shortest path algorithm, where the shortest path is the cheapest path, because each node is going to charge some fee, and so you can figure out the network topology and figure that out. And it also allows decentralized off-chain exchange. So more use cases. Gnosis is the prediction market. It's an application network, and so in this case they have market makers that open state channels with many users, and they act as the hub. Initially it's centralized, there's only one market maker, which is Gnosis, but Gnosis plans on decentralizing, opening it up to allow anybody to operate a market maker, and they also plan to integrate with Raiden as well. And so another exciting project is one that's being worked on by Jahan Trembeck, who is a software engineer in San Francisco. And he's building Alethea, which is incentivized mesh internet. And it's like pay as you go for bandwidth. So if I wanted to use Galvanize's Wi-Fi, I could just pay some micropayments, and he includes the signatures for the payment channel in the packet headers, which is pretty amazing. Metamask, which is our Chrome extension, is going to have a pay-as-you-go API so that users can pay to use the service as a go, and it's going to team up with our infrastructure hub, Infura. And so essentially, Metamask is a user of Infura, and so Infura is charging, Infura is like clusters of Ethereum nodes and IPFS nodes and stuff like that. And so people can just charge as they go, and Metamask essentially is a user, and so all the users of Metamask get the fees from Infura and Metamask passed on to them, and totally simple. And so there's some next level shit, and that's a plug and play generalized state network. It's like Raiden, but for any type of state update. And so this is more in the sense of libraries that we can build, and having it so that every application doesn't need to build their own from scratch. Programmable state channels is when, if we think about it, when we have a state channel, what we have is data, code is data. What if we put code in the state channel? That would be interesting. The simple case is to have data that points to existing addresses and contracts on Ethereum. And so you could have, for example, a state channel that triggers some set of calls to another set of contracts, and if all of those contracts return true, then that's the validation condition, and this can be updated within the state channel itself, and it can be, as long as there's agreement between both people, then it's fine. The harder mode is like writing contracts directly in the state channel state. So instead of, you're passing back and forth like parameters of some balances, instead you're like actually passing back and forth like contract code, and that is essentially when it executes on Ethereum, it can do anything. There's some thoughts about thinking about state channels as the simplest form of ConsenSys. And so you're taking some data on the Ethereum blockchain and you are saying this specific piece of data can only be updated by a 2-of-2 signature from these people. And if you expand that, then you get this sort of like, if you get 3 people, then all of a sudden you need a consensus algorithm. And so you essentially can use Ethereum state channels to build sidechains. Thank you. That is all. Any questions? Yes?
Will you be able to get access to some of your slides somehow?
Yes, I will post my slides to the meetup as well as the code examples that I used. Yes?
So a question, you said like you can never do a state channel, right? Like you can close a state channel. And what happens if one of the person like dies? Like how the balance how is that settled? Right?
Yes. So the question is, how is a state channel settled if somebody dies or goes offline permanently? And so in Raiden and in many implementations, there are also time locks. And so if somebody else does not respond within a certain amount of time, you can close out the channel yourself.
So I can kidnap somebody and just kind of like keep them offline until I settle like with my data.
Yeah, hopefully that there isn't that much money in the channel, and that it's worth doing that. If you're going to kidnap somebody, try and get their private key. It's probably more valuable. In the back.
Yeah, something like a prediction market. How does state channels still work with parties doing it?
Could you repeat the question?
Yeah, what happens if parties join a state channel at different times, like individually?
Okay, so the question was like, how does a state channel work if people join at different times? And so what's actually happening is that every state channel exists only between 2 people. And so there's, in my example, I had an open function, and then sometime later you call a join function, and that's how you initialize it. So that is people joining a state channel at different times. I don't think that's actually what you're asking. So for Gnosis, the way it works is that they have a set of, so they have a market maker, and everybody sort of creates a channel with the market maker and then conducts all their trades with the market maker directly. And so it's not very important if more people come later, because they're all trading with the market maker, and the market maker is the person who is adjusting the payouts of the prediction. Yeah. Okay.
Who's going to dictate what the fees are for transactional?
Yeah. So for something like Raiden, it's an open network, which means anybody can join, which means it'll get set by market forces. Like the code is open source. You can run your own node. The things that will make nodes valuable are access and liquidity. And so what that means is every time you open a payment channel, you've got to keep some money in that channel for every person that you have a channel open with. And so who can provide the cheapest liquidity will charge lower fees. And if you imagine that there's this like big graph of people who you could potentially route through, the people who are going to earn the most money on that network are the people who are in the greatest number of shortest paths, where shortest paths also cheapest paths here. And so there's going to be competition within the network to set fees and try and be routed through.
Is it going to be like first data where they charge 2 to 3%, or
I think it's probably more likely to be fixed fees for asset transfers. Brent.
Can you talk more about how state channels are implementing an infrastructure platform like Ethereum and how those interact?
Okay. So the question was, can I talk about how Infura uses state channels? And so Infura uses state channels in 2 ways. So Infura is our infrastructure project, a cluster of IPFS nodes and Ethereum nodes. And so one way that Infura uses state channels is just to implement a pay per API call setup so that you don't really need an account. You can just pay as you go for the API calls based on the resources that you're using. Another way is Infura itself might serve RAID nodes, and it might also have pub sub aspects for message passing, because once you implement your application using state channels, then you just end up doing a lot of message passing between people. And so Infura could implement that also. Over there.
Has there been any talk around cross-chain state channels? So, let's say Bitcoin and Ethereum using smart contract exchange trading or something?
So the question is, has there been any thought about cross-chain state channels, maybe by combining Lightning or Raiden? There has been thought. It's not very far yet. I mean, neither of those platforms are released, so I think they're thinking about other things. It remains to be seen. It's active research area.
Theoretically,
there are a couple of systems that are trying to achieve cross-chain compatibility. So Interledger is one, Cosmos is another. I'm not sure, honestly. Talk to me more after. I'll tell you the little I do know.
when you request a channel, there's that period of time where it's a task result. So 2 questions. One is, what is that period of time? And the other one is what parties are responsible for technical ability?
Could you repeat the second part of that?
Like, what party is expected to check the validity of the
Okay, so 2-part question. First part was, how long is the challenge period when a state channel is being closed? And the second part was, who is responsible for being the watchdog in this scenario? So the answer to the first part is that it's configurable. I think in Gnosis it's like 30 minutes. I think in Raiden it's like 2. But that's just because there's a lot more trades, and this could change. In the second part, it's in the simplest case, it's just person A and person B, the people who are part of the state channels themselves, the participants. But it doesn't have to be them. The state channel can be configured to accept valid challenges to the state from anybody, as long as it is signed by both participants. And so to accomplish that, if one of the participants doesn't want to watch the Ethereum blockchain at all times, and then they could send the states in their channel to some kind of service that watches the blockchain for them. Could you speak up? How does state channels work for data oracles? What was the last part? That was it? So if the data needs to be used on chain, then you can't do it over a state channel.